Welcome to the video key for Quiz 4. So in this first three questions, we're comparing three molecules and asking a question about their solubility. And as we saw in lab, solubility is largely a function of matching the IMFs of the solvent and the solute. So the two things we're trying to mix, if we can match their IMFs, they're more likely to be soluble in one another. So since the solvent in this case is liquid ammonia, we should think about what IMFs are present in liquid ammonia. So let's just draw an ammonia molecule, and let's draw it out in full rather than... Okay. So we can see if we look at an ammonia molecule, it's going to have, if we look at this, there's four groups of electrons on here. So this is going to have a tetrahedral electron geometry, which means that the shape of the molecule is trigonopyramidal. So it's going to be have a dipole moment, right? These bond dipole moments are not going to cancel because it's not a flat molecule. So it's polar. So it's going to have dipole-dipole. It's going to have dipole-induced dipole. It's going to have H bonding. And let's say for a second why that is, because it has a hydrogen bond donor here and a hydrogen bond acceptor, because we have to have a hydrogen directly attached to a nitrogen to have a hydrogen bond donor, and we have to have a lone pair, which I kind of, now you can see them a little better, a pair of non-bonded electrons on a nitrogen, fluorine, or oxygen. So we've got both those things. So ammonia molecules will hydrogen bond to each other. And of course, I also should put London dispersion interaction, because it's always true of any pair of molecules. Okay. So let's look at these molecules. Now, all of these molecules have polar groups. They have these hydroxyl groups, which are polar. And so the more polar we are, the better we're going to be able to do H bonding and dipole-dipole with this other very polar molecule. So if we look at this, we've got a hydroxyl there, and a hydroxyl there, and a hydroxyl there. So we got four of these, and each of those, there's lone pairs on those. There's multiple lone pairs. There's two lone pairs on each oxygen. And so we could have, for each hydroxyl groups, we could actually have 3 different hydrogen bonds. That's like 12 different hydrogen bonds could come off of this molecule to an ammonia. So we have lots of interaction with ammonia possible. We also have this hydrophobic core of the molecule here that doesn't really do anything for us, but that's the same on all the molecules. So what we're looking for is what's different. And what's different is this one has lots of hydroxyl groups that will really mix well with the ammonia. Coming over here, this is similar. It's got 4, but it's also got this extra nonpolar part that's not really going to do anything for us. So this is going to be less. So the most soluble would be C. So most soluble, we'll put this down here, a little C down there. The least soluble, we want something that's less polar, that's not going to have the ability to hydrogen bond with ammonia the way ammonia can hydrogen bond with other molecules of itself. So if we look over here, all of these have hydrogen bondings, but these two only have one group that can do that, so it's not as good as these two over here. And this one actually has this other, leftover nonpolar portion in addition to the one that they all have. So this has got all this nonpolar stuff that's not going to be able to do the polar stuff. There's only this little tiny polar piece here. So A would be the worst at mixing with ammonia. And now we're comparing a molecule of A and a molecule of B, and we can see that we've got something that can hydrogen bond. We've got a piece that's polar, so we're always going to have London dispersion, but in addition to that, we have H bonding, dipole-dipole, and dipole-induced dipole. There's no ions anywhere, so we don't have ion-induced dipole, so cross that one off. That's wrong. Okay, what's the sign of delta H for a process in which we go from a solid salt to ions in the gas phase? And so we have a name for this. We call this the delta H for lattice. So it's breaking up a lattice, so we're forming individual cations and anions in the gas phase. This is always a positive number because we're taking a salt crystal. I'll draw it in 2 dimensions. Just, of course, remember that it's a this is a cartoon. It's 2-dimensional, not 3-dimensional, and this is implying that it's simple cubic, and we might have other crystal structures other than simple cubic. But the idea is that the ions are touching if they're oppositely charged, and that's very favorable, right? We've got these ionic bonds here between positive and negative, and we're just going to blow this apart into the gas phase, so none of the ions are going to be touching. So we're breaking ion-ion bonds. Breaking bonds costs energy. So that means that it's going to be endothermic, right? It's going to cost us energy. We have to put energy in to get this to happen. So it's a positive number. Okay, and just to remember the vocab for that, if it's a positive delta H, we say it's endothermic reaction, right? We have to put energy in. We mix water that's 100 degrees C with water vapor that is 100 degrees C. And we want to find how much of the vapor condenses. So remember, we've got vapor here, we've got water here, but they're both at 100 degrees C. So can we have heat transfer? No. You can only have heat transfer if there's a temperature difference. So heat flows from hot to cold. So if they're both at 100 degrees C, we can't have heat transfer. So without heat leaving the vapor can't condense. So the answer is 0 grams of vapor condenses, and we don't need to know any of these numbers to know that. So the answer is E, none of these. Consider two salts, each composed of one cation and one anion. Which one would have the higher solubility? So KSP, so I'll just pick a salt at random. I'll use sodium chloride, but it could be any +1, -1, or +2, -2, or +3, -3, right? Anything like that is going to give us a 1-to-1 ratio of cation to anions, which is what the question asked. We have the solid, and we're going to be in equilibrium with aqueous ions. And so the KSP is the equilibrium constant. So it's products over reactants. So we have concentration of sodium at equilibrium, concentration of chloride at equilibrium, and of course we're going to divide, well, what's the concentration of solid? The solid's not in solution. It has an activity of 1. We never put solids in there. So there's our KSP. So notice, this is just like that nitrates lab. The higher the concentration of dissolved salts, the higher the KSP. Well, the higher a concentration of dissolved salts means it's more soluble. So higher solubility equals higher KSP. So the higher solubility is a larger KSP salt. Suppose you run an experiment, determine the equilibrium constant of a reaction at a variety of temperatures, and then you plot your results. And you've got the logarithm of the equilibrium constant on the y-axis and 1/t on your x-axis. So this is what you did for the Gibbs lab. It was the equilibrium constant you looked at was the KSP for dissolving potassium nitrate. So this one's a little bit different because here we're going to have a positive slope, and you had a negative slope. So how do we know how this relates to the value of delta H? Well, we use the Van Hoff equation, right? So it says the log of K equilibrium is equal to negative delta H for the reaction over R times 1/t plus delta S of reaction over R. So notice, if we write this out as y equals mx plus b, this is y and this is x, right? And we can see that from our axis, right? That we plotted 1/t as our x-axis and log of k as our y-axis, and so that means that this must be m, right? If it's a line, it's got to be y equals mx plus b. So that tells us that our slope is the negative of delta H over R. So since we have a positive slope and there's a negative in this equation here, that m is equal to minus delta H over R, we can see that if the slope's positive, delta H has to be negative. So that would mean that it is delta H is negative, and that's the same as saying that it is exothermic. Okay. A little bit different for your data in lab. You had a negative slope, and then you had a positive delta H. A reaction has a negative value for delta G standard. What does this imply? So there's a couple ways to do this. You can do it without any math. You can remember that delta G standard being negative means that your product favored reaction In other words, you have a lot of products at equilibrium, or you can say K equilibrium is greater than 1. And you can actually see this too by using this equation that delta G standard is equal to negative RT log of K equilibrium. And because of the properties of logarithms, the only way to make delta G standard negative is if K is greater than 1. So with that said, we say that delta G standard being negative is equilibrium constant is large. We can't say anything about spontaneity because that's delta G, not delta G standard. Okay, next 3 questions. Refer to the plot on the screen and assume that the extent of reaction is 0.9. So let's go find that plot. Okay, here it is. I'll shrink down so we can see this a little bit better. And during the quiz, I put a little dot there because remember we said we were at 0.9. Okay, so the state of the system is here. So let's just analyze this and then we'll put our answers on the quiz. So looking at this, we've got pure reactants and we've got pure products. So we can see that as the reaction proceeds, we're slowly converting some of our reactant molecules into product molecules until we just have product molecules. Okay, so notice we can circle the start and say that we had pure products. So this is the Gibbs energy of the reactants, right? We had reactants at the start. And we could put a little pure sign there, right? So the Gibbs energy of reactants is on the left because we just have reactants on the left. And the Gibbs energy of pure products is on the right. So the difference between those two numbers, we do final minus initial, is going to be delta G standard or delta G pure, right? We're looking at the difference between the energy of pure products and pure reactants. So it's products minus reactants, so we get delta G standard. So we can see that's a negative number. But delta G is the sign of the delta G where you're at. So in other words, we said the state of the system is given by the dot, and delta G is a slope. So over here, delta G, the slope of that is a positive number. Delta G is positive. Okay. What does delta G positive mean? It means the reaction is not spontaneous in the backwards direction. You can see it's going to have a tendency to go down in energy, which is to the left, right? Not forward. So the backwards reaction is spontaneous, but the forward reaction is actually not spontaneous. Okay. One other question we're going to face is the equilibrium constant, but we just saw there was a relationship between equilibrium constant and delta G. Another way of looking at this is saying, notice that K is, products over reactants. It's going to be big if you have a lot of products at equilibrium. And where's equilibrium? Here. So notice equilibrium is here, and it's over to the right-hand side, right? We have more products than we do reactants at equilibrium. So we can either get that by the visual that the equilibrium lies to the right. This is greater than 0, so it should say greater than 1. Or you can do it mathematically by saying if delta G standard is negative, that means I have a big equilibrium constant. So going back to our answers, we can just circle that delta G standard was negative because overall our reaction, the products are lower in energy than the reactants. Delta G depends on where we are. This is the one that actually depends on where we are in the curve. So for the other ones, the answer doesn't, that dot could have been anywhere, and the answer to number 9 and 10 and 11 would be the same. Let's go ahead and circle this. We said it was going to be greater than 1 because these are linked. These have to be linked, right? So if delta G standard is negative, you're always going to have an equilibrium constant that is greater than 1. But this other one, 10, depends on where you are in the curve. It depends on what's the composition, what's the concentrations in that beaker. And we saw the reaction was not spontaneous in the forward direction. Indeed, it was spontaneous in the backwards direction, so delta G was positive. The slope of that curve was positive at that point. Okay. So just to hammer this home, delta G is the only one of those 3 that's point specific, that depends on where you are at a specific moment in time. The other 2, they would have been the same answer no matter where we put that dot. Okay, what is the sign of delta S for this process? And the process is we're going from salt gas to salt aqueous. So we're taking ions and they're free to move around in the gas phase. They're flying around, and then we're putting them into water. They're not as mobile, so the ions' mobility is going to be less. But also, remember, when we put ions into water, we're going to orient the water molecules around those ions. Orient water molecules, and that's a huge effect. Okay, so not only decrease the entropy of the ions, we decrease the entropy of the water molecules when we put ions into it, because they get oriented either towards or against. The dipole of those molecules gets oriented towards, or of those water molecules gets pointed towards or away from the ions, depending whether they're positive or negative. So this is always going to be negative for any salt. Okay. That's if you're going from the gas phase to the aqueous phase. Okay, suppose we mix water that is at 20 degrees C with water vapor that is at 100 degrees C. What parameters do we need to find the final temperature? So let's go ahead and draw a little TQ curve. So we'll have Q here, we'll have T here, and we're talking about water. All three phases are, in principle, could be present. Let's make this a little smaller. Okay, now we've got water at 20 degrees. Let's label this. This is solid, liquid, and gas. So 20 degrees, that's above the melting temperature, but below the boiling temperature. So we'll put it like sort of right in the middle here. Okay, water vapor is at 100 degrees. That's right at the boiling temperature. So know what's going to happen. Those temperatures are different, so you're going to lose heat from the water vapor, and it's going to go into the liquid water. So we're going to do some heat transfer there. And the liquid water is going up in temperature, so we've got Q for the water is equal to M water, C water, delta T for the water. And if we look at the vapor, Q for the vapor is going to be how much vapor condenses in terms of moles and the heat of vaporization. And we got to be a little bit careful here. Heat of vaporization is for boiling the water. We're not boiling it, we're condensing it. So we're going to put a negative sign on there. Okay, so we can see which parameters we're going to need. We need the heat of vaporization. So that is over here. We're going to heat up the water. So we need the specific heat of water because the water is below the boiling point. We don't need the specific heat of the water vapor because you can't have water vapor below 100 degrees. And so the water vapor, instead of cooling down, it just condenses to liquid water. So that's why we have this term, but we don't have a MCAT term for the vapor, okay? Because it's not going to change temperature; it's just going to condense to water. Okay. So next one, we have some colligative property problems, and so we've got delta T for boiling is equal to I times a constant, we'll call it KB, times the molality of the solute that we put in. And so we make boiling points higher when we put stuff in dissolution, we make freezing points lower. But in every case, it's a function of how many particles are in a formula unit, and we also have to know the concentration. And there's the case constant is going to be different for every solvent. Okay, so we do a lot of stuff with aqueous solutions, and those constants are on your equation sheet. So here, notice the concentration, the molality was the same. These are all 0.5 molal. However, we've got I equal 1, because this is just a molecular compound. We've got I equal 2, because you form a potassium ion and a chloride ion. And then we've got I equal 3, because you get a calcium ion and 2 chloride ions. So this is going to be the one with the biggest effect, because the concentrations are all the same, but this has a bigger Van Hoff factor I. On the bottom one, number 15, I put in things where the Van Hoff factor is all the same compound. Van Hoff factor is 2 in this case. So it's all about concentration. So we see we got high concentration, mid, low, and so this is going to be the biggest effect, and so that is going to be the one that freezes at the coldest temperature. Okay, the last one, this sort of relates back to our heated combustion lab where we combined a bunch of reactions, and we have to figure out a way to combine these reactions to get the third reaction. Because we have known heats for the first two, we want to figure out what the heat of reaction is for the second one. And one thing to do here is look for differences, right? So we can see and similarities. So we look and we see, okay, I see chlorine here, and I see it in my target reaction. So it looks like I need reaction 1 once over. So I'm going to say reaction 1 times 1. Okay, and let's see if there's other things I can find. Okay, the C2H4 is in both, so that's going to be too confusing. Let's not use that as a key to this puzzle just yet. We do see water only appears in one place, here and in our target reaction. But notice in our target reaction, it appears twice over, and it appears as a product minus not a reactant. So that means we're going to have to put a minus sign in front of our reaction number 2. Okay, so my claim is that if we do that, we'll end up with reaction 3. Let's see if that's actually true. So let's write reaction, let's go ahead and write reaction 1, because we said we're going to have that in the forward direction. So we've got C2H4, that's ethylene, and we're going to have chlorine, and we've got C2H4 Cl2. So we've got dichloroethane there, and that's delta H1. And then I'm going to go minus 2 times reaction, actually I'll just write that over here. I'm going to subtract reaction, oh geez, that's not what I wanted. Let me write that back. Oh, that's not what I wanted either. Let's try that one more time. Draw, okay. This was reaction number 2. Okay, so let's write reaction number 2, and we're gonna write it backwards, right? So it's minus 2 times delta H 2. So we have to write it backwards. Okay, so the backwards for reaction number 2 and times 2. So we have 2 C2H6O. So we just took this and put it on the other side, because that's what that minus sign means over here, and we multiplied by 2. And then we're going to have 2 waters. We're switching sides on the water as well. And then we're going to have 2 ethylenes, C2H4. Okay, so if we're right that we're taking the first reaction and taking the second reaction, multiplying it times 2 and subtracting, then this should cancel to give us our target reaction. So we look at this, oop, this is supposed to be Cl2. Let's fix that. Okay, so looking at this, there are things we can cancel and things we can't. So the chlorine doesn't cancel, right? It just appears in one place. Our C2H6O only appears in one place. So let's just write that down. So 2 C2H6O. And we've got our chlorine, which only appears here, so we can't cancel that. What about this? Well, if we look at our C2H4, there's 1 mole there, and there's 2 moles there. So if we subtract 1 mole from both sides, we can see that that cancels. Oh, I canceled the wrong thing. Oops, let me go back. There we go. It's over here. We're going to cancel 1 mole. Oh, man, driving me batty. Okay, we're going to, there we go. We're going to cancel one of those. So that means on the right-hand side, we're only going to have 1 C2H4. What else do we have? Well, the water only appears in one place. So we can go ahead and write 2 moles of water over here. And our C2H4Cl, that only appears in one place as well, so we can write that. Okay, so looking at this, let's see if this matches our target reaction. 2 C2H6O, yes. 1 mole of chlorine going to 1 mole of ethylene, 2 moles of water, and 1 mole of C2H4Cl2. Okay, great. So this is our reaction 3. So this is delta H for reaction 3, and we can see it must be equal to delta H for reaction 1 minus twice delta H for reaction 2. as we had said. So it's this. So let's go ahead and circle that answer, reaction 1 minus twice over reaction 2. So that's C. All right, that's it for the video key for quiz 4. Thank you for watching.